This video is brought to you by mywayteaching.com.
Next topic is Gibbs energy change and equilibrium. So in that Gibbs energy, we know what you know now. You are having some idea about what do you mean by Gibbs energy change. Okay, now I will explain change and equilibrium. So we have seen how knowledge of the sign and magnitude of the free energy change of a chemical reaction allows. The first one is prediction of the spontaneity of a chemical reaction, and the second one is prediction of the useful work that could be extracted from it. Okay, and the term reversible indicates that a given reaction can proceed in either direction simultaneously, so that a dynamic equilibrium is set up. This means that the reactions in both the directions should proceed with a decrease in free energy, which seems impossible. It is possible only at equilibrium, only if at equilibrium the free energy of the system is minimum. Okay, when there is a free energy of the system is minimum. If it is not, the system would spontaneously change to configuration of lower free energy. So the criterion for equilibrium, that is A plus B, we know that C plus D, that is delta R into G is equal to 0. Gibbs energy for a reaction in which all the reactants and products are in standard state. So it is delta R standard, delta R, this one, that is related to the equilibrium constant, related to the equilibrium constant. Okay, so the reaction as follows, I will write here: 0 is equal to delta R G plus RT ln K, or delta R minus RT ln K, or is equal to minus 303 RT into log K. We also know that delta RH is equal to minus RT into ln K. Okay, so this is about Gibbs energy for a reaction in which all the reactant products are. Next here, that is now you consider delta RH, delta S, delta RG. So and its description, when this is minus and this is plus and this is minus, reaction spontaneous at all temperature, and this is reaction spontaneous at low temperature when all are minus, and 2 minus non-spontaneous at high temperature, and all are plus the non-spontaneous at low temperature, and this is reaction spontaneous at high temperature, and this is reaction non-spontaneous at all temperatures. Okay, this is effect of temperature on spontaneity of reaction. Effect of temperature on spontaneity of reaction. Effect of temperature on spontaneity of reaction. Next problem. So calculate the delta Rg for conversion of oxygen to ozone, that is ozone at 298 Kelvin, if Kp for this conversion is 2.47 10 raised to minus 29. We know that solution. Okay, now it is solution. We know that delta R into G is equal to minus 2.303 RT log Kp, and where R is equal to 8.314 kilojoule per Kelvin per mole. Therefore, it's equal to minus 2.303.314 joule per Kelvin per mole into 298 Kelvin log of 2.47 into 10 raised to minus 29. They are giving the value, so that this will becomes, after calculation you are getting 163 kilojoule per mole as the answer. Okay, next problem. Find out the value of equilibrium constant for the following reaction at 298 Kelvin. That is 2NH3, and this is carbon dioxide, and which gives NH2 CO NH2, that is in aqueous plus H2O. This is a problem, and standard Gibbs energy changes at the given temperature is minus 13.6 kilojoule per mole. For this, solution is, we know log K is equal to minus delta R into G divided by 2.303 into RT, and substituting the values minus 13.6 into 10 raised to 3 joule per mole divided by 2.303 into 8.314 joule per Kelvin per mole into 298 Kelvin, which gives 2.38. Hence, K is equal to anti-log 2.38 is equal to 2.4 into 10 raised to 2. Okay, next problem. At 60 degrees Celsius, dinitrogen tetroxide is 50% dissociated. Calculate the standard free energy change at this temperature and at 1 atmosphere. Okay, solution. Okay, if dinitrogen dinitrogen tetroxide is 50% dissociated, the mole fraction of both the substances given by N2O4 1 minus 0.5 divided by 1 plus 0.5. 2 into 0.5, 1 plus 0.5. So, into 1 atmosphere, like PnO2 is equal to 1 divided by 1.5 into 1 atmosphere. The equilibrium constant P is given by, that is Kp is equal to PnO2 whole square, that is 1.5 divided by 1.5 whole square into 0.5. You are getting 1.33 atmosphere pressure, since delta R ln Kp is equal to minus 8.314 joule per Kelvin per mole into 333 Kelvin into 2.303 into 0.1239. So you are obtaining minus 763.8 kilojoule per mole. Okay, this is the last problem in this chapter. Okay, and Gibbs energy change and equilibrium is the last concept. Thank you.